All right. Hi. So I'm just going to start off by trying to find out if people had a chance to go through what we started discussing day before yesterday. So before we proceed, I just wanted to find out if you have any questions. We started our discussion of trying to highlight exactly how texture encoding takes place, right? So we latched on to a specific character set, that's the ASCII encoding scheme, and we discovered that that in fact each of these individual characters that we tend to play with, or that we use to create complex data or texture content, like for instance, when you're writing an assignment, essentially are based on an encoding scheme, or we can vaguely perceive it as being based on an encoding scheme that is that uses 256 characters as a basis, right? So whether you're writing a 10-page assignment or could be like maybe a 100-page report, assuming it's text only, what we're saying is you could potentially end up playing around with this sort of character set. More importantly, though, we discovered that that in fact this character set is designed in such a way that there is a mapping between the the different characters that comprise the character set and equivalent binary representation, right? So usually, not usual actually, there's typically a table, right? Like in the case of ASCII, there's an ASCII table that highlights exactly what sort of hexadecimal and decimal representation is used to map onto specific characters, right? And we had fun looking at how 0 is represented, right? It turns out that 0 is not, the computer doesn't see 0 as a continuous stream of 8 zeros, but rather it's a hexadecimal number 30, right? So I don't know if people have any specific questions with regards to this, but I thought it was pretty intuitive and really straightforward. Also interesting, I guess, in my opinion. So if there are no questions.
Dr. Layton.
Yes, sir.
So the idea of if you're given a question like convert and decode these streams of bits into maybe into what they are representing if we're using ASCII as our codec. So we just have to convert them to decimal and then check the mapping using the ASCII table.
Yeah, they're not codecs, by the way, but yeah, that's what you do, right? I mean, so the question will probably specify, if a question like that was ever to come, it will specify details of the bit representation that is used, right? So if it's ASCII, obviously, it would be like 8-bit representation. So the expectation is that given a stream, right, a continuous stream of, I'm just going to use octet as an example, given a continuous stream of ones and zeros, similar to what we were looking at for this text file that we created day before yesterday. Don't know if you remember this, but I remember myself. If you're given, let's say you're given this sort of continuous stream of data, you're told to say, can you decode this to its equivalent representation in textual format, right? Textual format representation. What you do is, if you know that it's 8-bit representation, all you do is you convert each of these 8 bits, right, segments here. You convert them to, so you start with the first one here, which is, I don't know if you can see my mouse here on the top right corner here. You notice that this is 0, 1, 0, 1, 0, 0, 1, 0, 0, 1, right? So what you do is you'd get that and then you decode. And decoding this is, I mean, so converting this to decimal is pretty straightforward, right? What you can do, usually, if you look at past exam questions that are associated with 1110, what you notice is that if there's a question related to data encoding, for instance, textual content specifically, you are given, you'd be given an ASCII table, right? So something similar to this, right? All you have to do is, if the ASCII table has both hexadecimal and decimal, you take your pick, right? So if the ASCII table that you have access to has both decimal and hexadecimal representation of the character, all you have to do is just try and figure out what is the hexadecimal representation of what's a hexadecimal representation of 01, 001? Oh, sorry about that. It's in insert mode, right? 01, 001, 001, right? What's a hexadecimal representation of it? And it's easy, right? The easiest way of splitting this up is to split them up into nibbles, right? Right? And then after you do that, this is ones place, twos, what's it, left to right, I guess, ones place, twos place, ones place, Jesus, ones place, twos place, fourth place, eighth place. So this is 9, right? I guess, I don't know. And then this is ones place, twos place, fourth place, 4, right? So like 49. So you know that this is a hexadecimal number 49, right? So you go to your, no need for us to convert the things, the symbols. So you go to your ASCII table, you come here and you look for hexadecimal number 49. Hopefully be able to find it somewhere. Can't see it anyway. There we go, it's here. I don't know if you can see this. 49 is I, right? Which makes sense actually, because that's what we're looking at. I don't know if you can see 49 here. Hexadecimal number 49 here. Right, so we know that if it's 49, then the first character, the first thing here, this is an I, right? And then you go to the next one. Actually, I guess the example kind of goes through this, but it's flipped the other way around, right? Where we are generating the binary representation of the characters, but it's the same concept really. You can do the opposite. If you can go the other way around, you can do the opposite, right? And then you go all the way up to the end, right? So it's not that hard. And then typically, sometimes the question might be phrased in such a way that you're given a continuous streams of zeros, right? It's so that we mimic exactly how a computer gets to see these things, right? Where you're given something like oh, you have this sort of representation, right? That should be fun. What would this be? 1, 2, 3, 4, 5, 6, 7, 8. What would this be, right? You wouldn't, so you're given a continuous stream of this, all you have to do is know that if it's ASCII, if it's an ASCII encoding scheme that's being used, then each character is going to be represented by 8 bits, right? So you just split it up into 8, and then you know that this is 2, 3, 4, 5, 6, 7, 8, right? And then you play around with it. I don't know what this is. This is like, this is nice. This would be like 2, 4. The first one would be like a 0, I guess. This is an obvious one. So this is 1 place, 2 place, 4 place, 8 place. It's like 12. Which is C, I guess. And then this is 0. So C0, right? So this would be like C0, right? Hexadecimal number C0. I mean, if we were to come up with the thing that I just came up with, and then you come to your ASCII table, and then you look for if you can find C0 or something. I'm sure you should be able to find it somewhere. This is just a partial representation. It doesn't have all the 256 characters. All you can do is you can go to your ASCII table, I guess, and then try and find C0 is the correct one. I think it should be a correct one. So you find your C0 hex C0. Can't find it. Anyway, that's essentially what you would end up doing. Anyway, I can't find it here, but we're not here to find C0.
I have a question.
Yeah.
So, for instance, you like the scenario that we have C0, and you don't have like the ASCII temperature in the very weak doesn't have a 0.
It will. It's supposed to have it. It should have it, unless it's done something wrong.
All right.
Yeah. It should have it unless if we've done something wrong, which we have probably. I don't know. I've just made up this thing here, right? This is so the other way of looking at this is maybe the ASCII table probably omits ASCII table probably omits the zeros or something. I don't know. Maybe like C or something. I don't know. But that's just some stray example that I just came up with. I don't know if there's something wrong with the example I came up with. I don't know. All right. So this is it, right? Not so hard. Text representation. So here's the thing, right? Just to try and consolidate what we talked about, this idea of encoding schemes, and specifically this is ASCII encoding scheme. Let's say let's say just hypothetically speaking, we wanted to figure out exactly how would generate the binary representation and how a computer would actually perceive, of course that's abstracted, but you perceive ICT 1110, right? How exactly do we get to a stage where we are here, right? And then we find ourselves here, right? With these continuous streams of 0, right? Well, if you have access to your ASCII table, it's not that hard, right? It's not that hard if you know the encoding scheme. So in this case, we're saying how is ICT 1110 represented using ASCII coding scheme? So we're making certain assumptions here. We are making the assumption that this encoding scheme makes use of 8-bit representation, right? And so we start off by generating the binary representation for each of the individual characters. Why? Because we know that each individual character is represented by a byte, and the byte is obviously represented by 8 bits, right? So all we do is we start peeling off. We start generating the binary representation, 8-bit binary representation of the individual characters. So you notice that we go to our ASCII table, I is represented by the decimal number 73 or the hexadecimal number 49, right? And so all you have to do here is either you take your pick, right? Choose your poison, either convert 49 base 16 to binary, or you can choose to convert 73 base 10 to binary, right? Usually, when you're given an ASCII table, if you have look up ASCII table, it will have numbers both represented in decimal and hexadecimal. It doesn't matter whether the characters have the representation in decimal only, or both decimal and hexadecimal, or in hexadecimal only. We've gotten to a stage where we know how to convert from decimal to binary or hexadecimal to binary, right? So straightforward stuff here. And hope you're seeing the link here, why we were doing some of those things before in previous lecture series. So we are saying is represented by 73 base 10. And so we go through a process where if I choose to use 73 base 10 to convert to binary, all I'm doing here is performing repeated division by 2, right? And then I'll generate 0, 1, 0, 0, 1, 0, 0, 1. But perhaps the simplest option here would be to just get the hexadecimal representation, which is 49, right? And then, anyway, choose your poison, whatever happens. I would go with hexadecimal, and then you convert it to binary. Why? Because each of the individual symbols, hexadecimal symbols, can be mapped onto 4 bits, right? That nibble. But it doesn't matter if you find repeated division by 2 to be desirable, you can do that, right? So you come here and you say, okay, it's I is 73 base 10. Then what I am going to do is I'm going to say I'll repeatedly divide 73 by 2, right? Where I have my quotient and my remainder here. One and the same. I mean, you just choose whatever you feel comfortable using here. Oh wow, this is where you actually need a calculator, but I guess I could divide by 2. So this would be like 37, right? Remainder 1 or something. 2 into 37 would be 18, remainder 1 or something. 2 into 18 would be 9, remainder 0. 2 into 9, the usual stuff, right, would be 4, remainder 1. Then, I mean, you go on and on. And at this stage, really, you shouldn't, 2 into 4 is 0, so it's 2, remainder 0. You shouldn't really have to worry so much about this because it's, sorry about that. So can I call you back? I'm in class right now. All right, thanks. Sorry about that. Somebody was trying to, I don't understand why people call email, right? So 2 into 4 is, it's confusing. People calling, right? Why do you call? Sorry about that. So 2 into 4 is like 2, remainder 0. 2 into 2 is 1, remainder 0. And then the usual stuff, right? 2 print 1, remainder 1, and then you find your answer, right? Until you notice that until 100, your answer will be, there we go. Beautiful. So this is what I wanted to showcase here. So your answer is 100, 101, 1, right? But of course, because it's 8-bit representation, remember what I said? Prefix with a 0 at the beginning, right? And so you have this 0, 1, 0, 0, 1, 0, 1, 1, right? And then you come up with this, right? Right. So here's the thing. I mean, so you identify the bit representation for the binary representation for I, which is quite easy with ASCII table. You do the same thing for C, right? All you're doing is you're doing a lookup here. Notice you come to C, you realize that C is represented by the decimal number 67 or hexadecimal number 43, right? And then you come to your T, right? And here's the other thing. Remember that for the ASCII table, lowercase t is different from uppercase T, right? So each one of those different characters are represented by a different binary pattern. And it makes sense because the computer needs to know, right? As a human being, perhaps you know intuitively, I guess, that whether it's uppercase A or lowercase a, it means the same thing. I mean, the context might matter, but it means the same thing, right? And semantically speaking. But as far as the computer is concerned, you're talking about completely two different things, right? And so you have different representations for both uppercase letters and lowercase letters. So you come to uppercase T and you notice that it's represented by hexadecimal number 54, perhaps decimal number 84. And then you just convert this to binary, right? You come up with that answer there. And then you come to 1, right? Again, I guess, point to note here is that the numbers, it's not like the numbers are represented in the binary form by just converting the actual number to binary, right? So we don't, what we're saying is that you must not assume that 5 in binary using the ASCII table is derived by repeatedly dividing 5 by 2 so that you get the binary representation. No. In the ASCII table, these symbols, they're not numbers, the symbols, the decimal symbols 0 through 9 are represented by specific numbers, right? So in this case, you notice 0 is represented by 48 base 10, but we're interested in 1 here. 1 is represented by 49 base 10, right? So we convert 49 base 10 to binary using 8-bit representation, and then we'll come up with this answer there, right? So again, we are still dealing with 1 here. Dealing with 1. And of course, for a little while, somebody was asking for a link to the class that we have. So can you send the link? I sent the link. I don't know. Can you just give me a second? Let me see if the link is there. It is there. Confused characters. All right. So 1, right? And then another 1 there. It's still 49 base 10 to base 2. Using 8-bit representation, you come up with that answer here. And then finally, you come to the 0 symbol, right? 0 symbol is represented by decimal number 48 or hexadecimal number 30. And then you just convert it to binary using 8-bit representation. Quite easy when you decide to use the hex symbols. Why? Because all you do is you split up the hex symbols, you convert the individual hex symbols into binary, right? Using 4-bit representation as nibbles, essentially. It makes life a lot easier. In my opinion, instead of going the other way around where you convert the decimal to binary, right? Because you'd have to repeatedly divide by 2. But whatever works for you, it's fine. But here's the thing. You notice that this ICT 1110 thing here has a space, right? And the space, character, it's a character. It's identified as a character. It has its own separate representation, just like these other special characters that we have, right? So the ampersand, the percentage sign, the parentheses, the braces, right? All these things that you find on your keyboard, right? And we talked about some of these things here. Parentheses, opening, closing parentheses, these are all represented separate in ASCII. Opening curly brace, or opening brace, closing brace, backslash, forward slash, all of these things, right? The pipe symbol, all of these, I guess, plus sign, equal sign, all these things are represented by their own binary pattern, in whatever encoding scheme you're using. So in this case, in ASCII, all of these things are their own separate representation. And this makes sense, right? Because what we're saying is that the bit patterns, they form the basis, the building blocks for us to create complex content, in this case, complex textual content. So imagine a situation where a person like Lighton writes something like this, right? He writes something like, he prepares something like this. Think about this for a second. He prepares something, forget the images here, but he creates something like this. What makes all of this interesting is that fundamentally, you could view this entire document, this 4-page document, as having been composed or authored using 256 characters, 2 to the power 8, right? And each of these individual characters, the C and whatnot, these are represented using their own binary bit pattern, essentially. I don't know if this is making sense here, but I thought I would kind of rub it in here and try and showcase an example. And lo and behold, at the end of it all, what we're saying is that a computer should be able to represent content like so. And we've kind of like formatted it in such a manner that it's easy to interpret, but ideally there shouldn't really be any spaces, right? As far as the computer is concerned, it's just a continuous stream of 1 and 0s. Yeah, it's interesting, really, if you think about it. So this is something that I guess you'd say a computer would be able to see, really. Of course, I mean, it should be like electric signals, right? Not really actual 1s and 0s. Flow of current and non-flow of current. All right, and then again, I do encourage you to play around with some of this application software that I showcased, right? There are a number of hex editors that are available out there. The best option I've been able to find, at least for Ubuntu or KDE, Kubuntu Desktop, is in my case is Octeta, but there are a number of hex editors that you should be able to find. Some of them that are specific to Windows. I'm not sure if Octeta can be used on Windows, but I'll leave it up to you to decide. Is this making sense?
Yes, sir.
All right. And again, just to kind of like showcase the same example, the ICT 1110 example here, ICT space 1110 and uppercase I, uppercase C, uppercase T example here, you notice that this is something we spoke about dead first today, but just to rub it in here, I was showcasing the fact that if you look at, if we create a file, right, a file that has this content, textual content, ICT space 1110, we can do a couple of interesting things here. Aside from viewing the contents using a hex editor, so that we're able to see the binary representation of the content, like so. What we can also do is go a step further and try and latch on some of these ideas we introduced a couple of series ago, to try and check how much space is associated with this content. And at this stage, we can determine the amount of space that a file like this would occupy on disk, on persistent storage, because we know that according to ASCII encoding scheme, each character is a byte in size, right? So it's represented by 8 bits, which is a byte in size. If each character is a byte in size, then what we're saying here is we have, how many characters we have in ICT space 1110? It's 9. I don't know if it's 8 or 9 here, but it's 8, right? I guess, I don't know. So we expect it to occupy 8 bytes on disk, right? And this is what we're showcasing here. We're saying we have this text file here.
Yes,
we created this text file, and all we do is we just count in the number of characters. Each character occupies 1 byte, so we have 8 here, including the space, by the way. And then we have 8 bytes, and we can see here, right? If you look at the highlighted portion of this file here, you notice that it's occupying 8 bytes on disk. All right. Right, but it turns out really that some complicated applications, right, would typically, more modern applications would typically allow you to explicitly state which encoding scheme you wish to use as you are creating content, right? Because as a user, one of the primary things you do, or at least some people anyway, is you create content, right? Maybe you're working on an assignment, it's in Excel or something, you're creating content, you're generating content. Now, the reason why these sophisticated applications will explicitly ask you to specify an encoding scheme is because they are designed to be used by different types of people, not just Zambians, Chinese, Japanese, right? All these other individuals or human beings who typically use languages that have characters that are outside the confines of the English alphabet. Right, so a way to easily accommodate those strange characters, right? I don't know if it's kanji or something. I don't know what they call this, but this is for you to be able to accommodate these characters here. You need a specific encoding scheme, right? And sadly, right? If you look up things like we'll talk about some of these things, but if you look up things like total number of Chinese, oh, there we go, Chinese characters. Okay, I didn't know it was 50,000. How about Japanese characters? Think about this for a second. If we are saying, if we take it by faith, this is from the BBC, I suppose, I don't know. They're saying the total of 50,000 characters. If it's 50,000 characters, and we've said that ASCII, ASCII, traditional ASCII has 256 characters, 2 to the power 8. Sorry about that, 2 to the power 8. And this will not be sufficient to represent the Chinese characters, right? You have to think about alternative character encoding schemes that are able to do this. And I don't know if you've got into a stage in Excel as you're exporting these things. So about the phone, I should have put it on mute here. In Excel, when you're discussing spreadsheet applications with Mr. Mwalimu, I don't know if you've got into a stage where when you're exporting things, right? If I was to export this thing that I was doing here, you notice that one of the things it will do is, especially if I'm, let's say, using a CSV format or something, and I know you've discussed this, but I'll just use it as an example. One of the things that you are, just home director, I guess, if I try and save this, observe, one of the things that it will ask me to do is character set that I wish to use, right? You see this? Can you see my mouse here? These different character sets here. Right, so if I'm from Turkey or whatever, I guess I'll choose one of these or something. Yeah, this is really important, anyway. Yeah, sometimes, I mean, if you use the wrong character set, you typically, the application software will signal. It will pop up an error or something. But the cool thing about application software is that they're usually default options that are wired within the application. So if you noticed, when I was doing a save as, the moment I decided to say I was going to save this as a CSV file, sorry about that, CSV file, the moment I chose CSV file and did save, you notice that the default option is what? Unicode, UTF-8, right? This is the best possible option. At least it's generic enough to accommodate most, right? Most of the different character sets. Right? But of course, I mean, if you know what you're doing, then you choose the appropriate one or something. Easy. Hopefully you've got into this stage. And this, by the way, this comes up in so many different areas. I'm just going to showcase something else to you. This you must see, right? Usually in applications, other applications like Moodle, for instance, when we are importing grades, for instance, if we are wanting to import grades, I don't know if I can do this, but if we're wanting to import grades here, if I can just showcase this, I guess, I don't know if this is going to work, but wow. If I'm wanting to import grades here, you see this? Encoding, right? Can you see this? Encoding. These are options that you see, right? I'm just going to zoom in here so that you see what I'm talking about here. I guess the key takeaway point is I'm trying to highlight the fact that this is such an important, simple yet important concept that you might need to understand, right? It's everywhere, right? And it's, I guess, probably the reason why, especially when it comes to creation of content, the reason why you haven't seen this is because you typically tend to go with the default options. But you see this in Moodle when you're importing files, you have to specify the encoding scheme, right? Oh, ASCII is here, right? UTF-8 and all this, the good stuff, UTF-7, UTF-6. All right. Oh, and again, I mean, so it turns out though that some encoding schemes are not true. One of the reasons why we have a number of encoding schemes is because the more popular ones, the generic ones, typically the ones that were pioneered by people from the West, for instance, are not sufficient to accommodate the many characters that we tend to find in these other languages, especially languages that are, I guess, in Asia, for instance, or Arabic in the Middle East, for instance, Chinese, I don't know if you call it Chinese here, but maybe there's another words, but Japanese. It's not sufficient because these languages tend to use significantly more characters than your average language like English, for instance, right? And so you need an encoding scheme that is more superior to the likes of ASCII, an encoding scheme that is able to accommodate more characters. And this is the thing here. The goal is to ensure that the encoding scheme that you are using is able to take into account the characters associated with whatever language you're using. So if you're using Japanese, obviously you know that ASCII won't work. If you're using Chinese here, then you know that ASCII won't work, right? Because ASCII, we're saying tentatively here that it's used to represent 256 characters, right? 2 to the power 8. All right. So if it's not sufficient, then you need to go for something that is able to do that, right? It turns out that one of the reasons why Unicode is used as an alternative to ASCII, for instance, is because it can be used to represent characters in these other languages, right? Now, we've always left this as homework. I think it would be nice to keep you on your toes. I'd like for us to go and look into or do a bit of research as to why we have different alternatives to UTF, right? So UTF encoding scheme here. Unicode encoding scheme, Unicode, there's Unicode 16, Unicode 8. Why? Why is it that we have these different encoding schemes? And you can see them from here as well. If I do a save as, you notice that, I don't know if you notice this. If I do a save as and then I try and save this to CSV, do a save, what you'll notice is that there's UTF-8, UTF-16, UTF-7. So what I want you to do is do a bit of research and find out why we have these different alternatives, right? Why do we have these different alternatives to Unicode? And is there an obvious advantage? Are there obvious advantages and disadvantages to having these different variations? If they are, then what are they, right? I'd like for us to have a discussion about this, hopefully day after tomorrow, seeing as tomorrow is a holiday, apparently. Happy 56th birthday, Zambia. Is this making sense? You want to think about this from the perspective of representation of characters. And here's the thing, if you look at Unicode 16, for instance, UTF-16, what you immediately realize is if we work with our formula, 2 to the power n here, you realize that if we use UTF-16, we'll be able to represent 65,536 characters. Now, if we were to look at what we had looked up earlier on, you notice that those number of characters would be more than enough to handle. According to these people here, they're saying that there's 50,000 characters, right? Chinese characters, apparently. So UTF is perfect for this, or Unicode would be perfect for that, right? So you want to think about this from that perspective. It's all about how your encoding scheme is going to be able to encode the characters into binary. It has to be able to sufficiently do that, right? Is this making sense? Are there any questions so far? Pause here and find out if there are people there. If they are there, I guess.
Well understood, sir.
All right. So now that we're done with text, I'm just going to wrap up this lecture session with trying to get a better sense of how exactly color is encoded. Right. It turns out that you can play around with bits and try and see exactly how you can represent colors, right? A nice way of thinking about colors is different ways in which we represent color, right? When it comes to digital content, we'll sometimes have black and white content, right? Sometimes we have grayscale. Sometimes we have what's called true color, right? So, right, where you have these other different colors that are represented, right? And it turns out that in all these different instances, you can play around with the bits to represent the different colors. Representing black and white is probably the easiest, right? Because all you do is you use one bit representation. You just say one is black and 0 is white. Simple, right? So whenever you have a black pixel, just represent that using 1. Where you have a white pixel, you represent that using 0, right? When you're dealing with somewhat complex colors, though, like grayscale, it becomes a bit tricky, and so you have to use additional bit representation. It's common to use a bit representation to represent grayscale, right? Where you have much more than black and white. So you typically have, and I hope Wikipedia has a nice color-coded. I don't know if GIMP has. Let me just check GIMP. I don't know if GIMP has a way of trying to represent grayscale. Nah, GIMP is probably a bad idea. Yeah, bad idea. Maybe I'm just going to go with grayscale. I hope Wikipedia has a really nice visualization of grayscale. Beautiful. So if you look at what we're saying is that if you look at this color palette on the right here, this is what we're aiming for here, this thing here. So the question is, how would you be able to effectively represent these different color variations here, where at the top here will probably be white and then at the bottom is black, right? But in between, you have shades of gray or something, right? It turns out that this is easily achieved by just using something like 8-bit representation, right? Where the intensity of grayness is determined by the number of bits, the number of 8 bits that you're working with, right? So the larger the number, the smaller the number, the more white it is. The greater the number, the more black it is, right? So as you're going through or maybe the opposite or something, as you're going through the spectrum here, you notice that you could have a 0 on top here, then you have a 1 here. And by 1 here, I mean like if it's 8-bit representation, then it's all 1s, right? So all 0s and then all 1s or something. And then in between here, you probably have a combination of 1s and 0s. And depending on the combination of 1s and 0s, you'd have something that is much closer to white or something that's much closer to black. And this is the thing here. The best way of thinking about the intensity, because you are used to decimal, is to think about this intensity from the perspective of decimal representation. Where you're saying if the number is much smaller, it's closer to, it's smaller. If it's much smaller, then it's going to be much closer to white. If it's much larger, then it's much closer to black or something. Right. And then for things like colored pictures or so-called true color, and it gets more complex than what we have here, but we're just assuming 24-bit representation, right? Where you would typically have, you think about this here, is if you're using 24 bits, you could easily view the 24 bits as being comprised of different variations of red, green, and blue, right? So you could say 8 bits is going to be used to represent red, 8 bits is going to be used to represent blue, RG. And then the other 8 bits is going to be used to represent green or something. And then all you're doing is what you were doing in grade 1, where you're saying, how do we create pink using red, green, and blue? I don't know, right? You have different combinations of those different colors. Do you remember you did that in primary school, right? Where, look at this, I'll use GIMP here. When you're saying, oh, we want, I don't know what we want now, but we want to create, what are we creating here? We want, how do we create red? Well, I don't know, but maybe we could RGB. How do we create red? Forget of the saturation, and I don't know what the V is here, but just concentrate on the RGB here. You notice that if we're creating red, it's 255, which is the maximum, right? 0 up to 255 are the numbers we're working with. They have to be 256, 8-bit representation. Yeah, 24 bits, bit depth. If we want to create green, how do we do this? Well, we work with the maximum number. So zero will be, red will be 0, but green will be 255. And then we have green. How do we create blue? Well, this is 0. This is going to be 255. And then we create blue. Look at the current thing here. How do we, I don't know what we create pink, but what happens when you combine, what happens when we combine, they asked you this, right? What happens when you combine red and green? 255, 255. I don't know. Oh, yellow. Wow, I didn't know this. So I didn't know that if you combine red and green, you get yellow. What happens when you combine red, green, and blue? Don't know. Isn't it black or something? I don't know. 255. Black, right? So listen, it's simple ideas or simple concepts, but extremely powerful, right? Because it's formed the basic building blocks of what we view as, what we perceive as human beings as being, oh my God, it's an image of a human being. Well, it's not, right? It's just a combination of pixels, right? With different intensities. Yeah, your hair is just pixels here. But I don't know. I don't know if this is modding out here. Oops, this thing is, what just happened here? Sorry about that. My machine is acting up again. Yeah, beautiful. All right. All right, so again, just to wrap it in here, I mean, if we're to again try and relate what we're talking about to what we've discussed already here, for black and white, you're just using 2-bit representation. And if we're to view this from the perspective of the magnitude you'll be working with, it's the numbers 0 and, well, so you could just come up with just something punitive to say 0 is going to be represented using, black is going to be represented using 0, and then white is 1 or something, or the opposite, doesn't matter. So the total number of colors that you can represent using 1-bit representation is obviously 2 to the power 1, right? So 2 colors. Remember that formula? If you're using 8-bit representation, it's 2 to the power 8, which is 256 colors, right? So for grayscale, for instance, what we're saying is, if we use 8-bit representation, then we can represent different variations of grayscale up to the magnitude 256, right? Which is quite interesting, 0 up to 255, essentially. When you're dealing with, this is what we're talking about, grayscale here, it's 0 up to 255, or a total of 256 colors, essentially. 0 through 255, where maybe 0 would be black, and then white would be 255. And of course, what we mean by 255 is not really, best way of viewing 255 is, it's this, right? A stream of ones, 8 ones. And then the black is a stream of 8 zeros. And then the intermediate shades of gray here will be a combination of ones and zeros. And then so black and white, grayscale, right? And then for true color, right, or colored photos here, what we're saying is we're using 24-bit representation, but using 3 separate colors in this case, for this particular example. Of course, it gets more complex, right? If you look at color schemes that are available out there. But to make it simple here, just assuming that these colors, the colored photos or true colors we're talking about, are represented using red, green, and blue, essentially, make it simple. if we're using 8-bit representation, what we could assume is that each of these individual colors is represented using 8 bits. Cumulatively, you're playing around with 24 bits. So depending on how you are varying these 24 bits, you will either get red, blue, green, or anything in between by combining the different colors. And we see this in so many different places here. So before I'm going to pause here, and then we'll continue this conversation in the time. We'll continue this conversation day after tomorrow. But here's the thing. I want to draw attention to the fact that for those of you that will be asking yourselves, why are we doing this, right? What's the point of all of this? Well, it's coming back to bite you, right? Very, very soon. It turns out when you're doing web development, for instance, I'm going to leave you with this. When you're doing a bit of web development, what typically happens is the way you define colors is you use hexadecimal representation. You can see this really. If you look at the top, I guess I will look at the, pay attention to this top part here, which is somewhat blue here. I'll turn it to red, I guess. I don't know if I can, or maybe the green one, the top part here. I don't know if I can see this, but I was hoping I could see this. Beautiful. Bad thing. Let me see if I can. If only I could play around with it, it would be much, much easier. Give me a second, just yeah, I was hoping I could, let me see if I can find something that is a lot easier to manipulate. So what I'm trying to say here is that some of these things, ideas we've been discussing here, are applied in so many different areas, like especially web development, for instance. I was hoping I could use a simpler, this is somewhat content info, simpler. If I can find the green somewhere, that would be good, but it doesn't look like, oh, there we go, it's here. So, so I'm using this color here. You notice, I don't know if you can see this color here, background color. You notice that it's represented using this thing here. It says that, oh, sorry about that. The background color in here. It's this color here. If you think about this for a second, this color is a hexadecimal number here, right? It's a hexadecimal number, and if you know your numbers right, you won't have, if you know the conversions right, you won't have trouble converting these different colors. So let's say we wanted, so this is 8. You notice if this is hexadecimal, then 8, 8, 8, right? Because each of these is a nibble, right? 4, 4, 4, 4, 4, 4 by 8 is what? 1, 2, 4. 6 by 4 is 24, right? For bit representation. The pound here simply means it's hexadecimal number here. But if we wanted to represent this using red, right? And if you know your colors right, all you do is you'd say, well, if it's red, then what I'm going to do is I'll make this 25, this is 0, and this is 0. If you notice this HTML notation, can you see this below here? FF and then zeros, huh? Here. You there? Anyway.
Yes, sir.
Oh, right, thank you. So if I come here and I use this notation, I want to turn the background color here to red, and I know what I'm doing. I'll just say FF, and then I'll say 1, 2, 3, 4. Boom, right? This is the essence. This is coming back to a really powerful concept, right? And if you know your way around, that you won't even have to struggle with color. But of course, I mean, life has become so easy now. There are color pickers out there, right? Like online, you can look up like online color pick or something, and then to be able to generate, there we go, right? To be able to generate your colors for you so that you don't have to struggle. But also, it's important to understand the basics behind whatever it is you're doing, so that you have more control. This is the thing here. It's all centered around control here. So I will. We should tell the UNZA, write to them and tell them, say, please change the background color to FF0000. That would be nice, I guess. Change it, and they'll think you're smart. No, they won't. If there are no questions, I guess I'll see you later. I have another class that I have to transition to.
Sir,
Yep.
just a reminder, sir, you haven't responded to our emails, and so our
Yeah,
quizzes are not
if
yet.
I haven't responded to your
good.
emails, then I haven't checked the mails yet. I will respond to them.
All right, sir.
All right, thank you. Till we meet again, thank you. Sorry, is there a question?
Yes. Is there a situation whereby you asked, for instance, the one who presented grade, you presented it in hexadecimal format, but they ask you what is that hexadecimal format representing? Like what color is it? So we don't get anything.
Sorry about that. Yeah, sorry. So I was saying that if such a question was to be presented to you, whoever is asking that question will tell you to, that's a nice question, we should ask it. We shall ask it, actually. They'll ask you, thank you for asking, we shall ask it. They'll give you a mapping, right? Thank you, Mlenga. And tell you to say, oh, red is represented using 25500. Blue is, black is 255, 255, 255, right? White is 0000. What color is this, right? So they'll provide you with a legend with the different, I guess, hexadecimal numbers or decimal numbers that represent the different colors. Otherwise, I don't think they would be able to ask you that question. Because if you think about this, right, some of these colors are so complex. If you play around with the color pickers, for instance, what you will realize is that there's countless combinations. Well, not countless, but there's a number of different combinations for RGB colors, true colors. Think about this for a second. You're talking about 2 to the power 24. So we're talking about 16 million different color combinations. Now, if someone was to ask you that question, they would have to give you, it would be sad, right? That'd be a sad way of asking a question. But they would have to give you a legend or something. I hope that answers your question. I don't know.
Yes, I do.
Okay. All right. See you when you see me. Just to mention that in case we don't meet on Sunday, quiz will be all the way up to page slide number 34, where we're discussing color encoding, right? Because our next discussion is going to be in image encoding, essentially. Okay. We should bring the question that Mlenga asked. Maybe we should. I think we should. We will bring it. I'll see you when you see me. Hopefully Sunday. If not, then Monday. Thank you. Bye.